Hi everyone, welcome to the first lecture on this course, Optoelectronic Material, Devices and Fabrication. In this course, we will look semiconductor material. When we think of electronic or semiconductor material, the first property that comes to mind is the resistance. Then according to Ohm's law, that is V is equal to IR, we can define the resistivity of the material and then we define conductivity. Based on that, we have three categories, that is the conductor or metals, the second one is semiconductor, and the third one is insulator. Then what is optoelectronics? It is the science of device that are based on a process leading to the generation of photon. We can generate light by using electron. The classic example is LED or laser diode. Or generation of electron. We can generate current by using light, by a photon. The example is solar cell and photodiode. It is nothing but the interaction between optics and circuitry, that is the light and semiconducting material. Let us study the optical absorption in semiconductor. In this kind of interaction, we have two categories. The first one is, suppose if the incident light on the semiconductor which then create the carriers in the material. Example is solar cell. And the second one is, if we can inject the electron or holes into the semiconducting material or device, then there will be a recombination of carrier will be take place in order to give light or photon. Example is LED. Before we look into these devices, let us first thing we going to look at the phenomenon of optical absorption. We want to know what happens when a light of certain energy, that is E is equal to h nu, is incident on semiconducting material. In case of semiconductor, we define its energy by its band gap, that is the Eg, band gap energy, which is nothing but difference between or energy difference between valence band and conduction band. Suppose if the energy of light is less than the band gap energy, then there is no absorption. The material become transparent, which means the scattering will be take place. The overall, there is no optical absorption if the energy of incident light is less than the band gap energy of the semiconductor. If the energy of light is greater than or equal to band gap energy, then there is the absorption of light. The material becomes opaque, which means essentially the absorption of light will be take place. When this thing happens, then it produces electron hole pair in the semiconducting material. You can abbreviate it as EHP, that is the electron in conduction band and holes in the valence band. We know that from the idea of bonding orbitals, it has been found that the valence band is completely full and the conduction band is completely empty. And also we know that from the concept of density of state and the Fermi function at room temperature, we found that most of electrons located very close to the conduction band edge, and the most of holes are located very close to the valence band edge. If energy of light is greater than the band gap energy of the semiconductor, that is the energy difference. This energy difference is equal to some excess energy. And this excess energy can be released either by electron or holes. It loses this energy by a process called thermalization process, either by heat or it can release energy in the form of phonon. Now let us consider the example or some typical values of band gap energy. We can define the band gap energy as in electron volt. 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule. Let us consider the example of silicon have 1.11 electron volt The band gap energy of germanium is 0.67, and gallium arsenide, cadmium sulfide, zinc oxide. And based on this is also we can define or we can categorize based on band gap energy as the semiconductor and insulator. If the band gap energy of the material is less than 3 electron volt, then we consider it as the semiconductor. If it is greater than the 3 electron volt, then we consider the material as the insulator. Now by using the formula, the Planck's equation, E is equal to h nu. Nu can be defined, the frequency of oscillation can be defined in terms of C by lambda. Here E is the energy of incident light, h is the Planck's constant, you know that value 6.67, 10 raised to minus 34 joule second, and C is the speed of light, you know the 3 into 10 raised to 8 meter per second, and it is the wavelength. By using this, suppose if the band gap energy of the material is 3 electron volt, then we can easily calculate the wavelength emitted by that material, that is the 400 nanometer. Any energy greater than 3 electron volt puts in UV region, and less than 3 electron volt we puts in visible region. Now this is the band structure of semiconductor. We know that this is the valence band which is completely filled, and this is the conduction band. Now this is the conduction band edge, and this is the valence band edge. This gap you call it as the energy gap or the band gap, which is the energy difference between valence band and conduction band. Now there are classification of semiconductor mainly into two group. The first one is direct band gap semiconductor and indirect band gap semiconductor. Here the energy release in the form of photon, purely released in the form of photon. Here the energy release dominantly as the heat. Why it is so? Let us understand. So this is the band structure. We know that valence band completely filled by electron, conduction band completely empty. We know that when an amount of certain energy is incident, that is the whether you may call it as the light energy or thermal energy, okay, incident on semiconductor material, then what happens, the electron after absorbing that energy they excite to the conduction band, or the electron excitation will be take place from valence band to conduction band. Now after this excitation, electron does not remain for a long time, and the electrons come back to the valence band, and then the energy difference is released in two waves. That is, you can release in the form of photon or you can release in the form of heat. Suppose if the energy is greater than the band gap energy, incident energy is greater than band gap energy, the electron may goes to this position, and then they can comes back by a process of thermalization and then come back to the valence band. And another case is also possible. Suppose here the whole will be absorbed energy of incident radiation or photon, and then they by process of thermalization they goes to the valence band edge and then excite to the conduction band. Now the example for the band gap, direct band gap semiconducting material is gallium arsenide, cadmium selenide, cadmium sulfide, zinc oxide. And the example for indirect band gap semiconducting material is silicon, germanium, gallium phosphate. Now this is very have application. Direct band gap semiconductor material have application in optoelectronic devices. They can be used as LEDs, solar cell, photodiode and photovoltaics. Now to understand the difference between direct and indirect band gap semiconductor, we look into the band structure of semiconductor. Suppose this is the band structure of gallium arsenide and this is the silicon, which is an indirect band gap material. This is the direct band gap material. In any element, electron can be treated as a wave. Quantum mechanically, we can treat electron by dual nature from uncertainty, Heisenberg uncertainty principle. We can treat the electron as the wave. Then we define it's a wave as the wave vector k, which can define the direction of motion of photon. If p is the momentum, then the momentum of photon is proportional to the wave vector k. That is, the momentum of photon can be represented as r is equal to h cross k, where h cross can be defined in terms of h divided by 2 pi. H is the Planck's constant, k is the wave vector. Now here the top of the valence band and the bottom of conduction band have the same value of k. This is the energy momentum diagram. Here the top of the valence band, it has some value of k, that is the wave vector, and the bottom of conduction band having the same value. Then h cross is a constant, the momentum is also same in case of direct band gap semiconductor material. But in case of indirect band gap semiconductor material, the value of k is different. The top of the valence band and the bottom of the conduction band have different value of k, which means the momentum is not conserved. Here the energy is also conserved and momentum is also conserved during the process of recombination. Here the energy is conserved but the momentum is not conserved during the process of recombination process, that is electron and hole. The result, the energy will be released in the form of photon. When recombination take place, then both energy and momentum is conserved, therefore it emit photon. Here momentum is not conserved. In order to conserve, a photon is also released in addition to photon. Okay, which means the transition from conduction band to the valence band is by or accompanied by the release of energy of photon in case of direct band gap semiconductor material. In indirect band gap semiconductor material, a photon is released in the form of heat. This makes it an indirect band gap semiconductor. Why it is so? Because the conservation of energy is not a problem in both direct and indirect band gap semiconducting material, but the conservation of momentum is not possible in indirect band gap semiconductor material, because the magnitude of momentum of photon in indirect band gap semiconductor material is several order of magnitude smaller than that of electron in a indirect band gap semiconducting material. In order to conserve momentum, or in order to compensate, the photon is needed, or in addition to photon, a photon is released. So this makes the difference between direct and indirect band gap semiconducting material. Here the table consisting from the periodic table, so we have consider both direct and indirect band gap semiconducting material, that is the diamond, germanium, gallium arsenide, zinc oxide, cadmium selenide, and band gap energy also is noted. You can study this diagram. Thank you very much.